Hi guys, can you guys hear me?
I can hear you.
Okay. Okay, so I am going to start today's lecture. So last week we learned about Ka and Kb. Ka is the equilibrium constant for acid and or acid dissociation constant. Kb is equilibrium constant for base dissociation constant. And this table are some conjugate acid-base pairs. Okay, so for this acid, after proton falling off, after deprotonation, you will have a conjugate base that looks like this. Okay, for this acid, you have this conjugate base, this acid, you have this conjugate base, so on and so forth. Okay, so these are the conjugate acid-base pairs. So we've learned about Ka and Kb, and the product of K and Kb for conjugate acid-base pair is actually an equilibrium constant for water. This is only true for conjugate acid-base pair. Okay, so this is the equilibrium constant for water. Please note that not any acid or base combination will give this, okay? Only conjugate acid-base pair. I'm going to put a star here, okay? For example, consider this conjugate acid-base pair, ammonia and ammonium, okay? Ka can be determined from this acid reacting with water, okay? So the conjugate base for this acid is going to be, a conjugate base for this acid is going to be NH3, okay? Kb can be determined from this reaction where conjugate base is interacting with water. Okay, so for this conjugate acid, so let's find the conjugate Ka for this first reaction. Okay, so the Ka is going to be concentration of product divided by concentration of reactant, right? Each raised to the power equal to the coefficient. So the Ka is going to be concentration of NH3 concentration of hydroxide divided by concentration of ammonia. Kb can be found from this second reaction where conjugate base is dissolved in water. Okay, so for Kb, it's going to be concentration of products divided by concentration of reactant, each raised to the power equal to the coefficient. Okay, NH4 plus times, oops, my mistake. I made a mistake. This will produce hydrogen. Okay. So then the product of Ka and Kb is basically this multiplied by this. Okay, so I'm just going to rewrite that. Times plus. And as you can see, NH3 concentration cancels out. Ammonia concentration cancels out. You are left with proton concentration times hydroxide concentration, which is equilibrium constant for water. So product of Ka, Kb equals to Kw is going to be very beneficial for you to find a known Kb, a known Ka when you know Kb, Kw, a known Kb when you know Ka, Kw. But this is true and only true for a conjugate acid-base pair. Conjugate acid-base pair. Okay, so if you have a conjugate acid-base pair and if you know Ka, you can find Kb. If you know Kb, you can find Ka. Okay, why? Because Kw is always 1.0 times 10 to the negative 14, as we learned in last class. Okay, let's do a sample. Let's try a sample exercise utilizing the equation that we have just learned. Calculate Kb for fluoride ion and Ka for ammonium ion. So for question A, we need to find Kb for fluoride ion. We can find Kb value if we know Ka value, okay? Since fluoride ion is a conjugate acid of weak acid, this is a conjugate base of weak acid hydrofluoric acid. So we can find its published known Ka value from the table 16.2, okay? Since Ka value for hydrofluoric acid, as you can see from here, is 6.8 times 10 to the negative 4. We can easily find Kb for this conjugate base by utilizing this equation up here, okay? So since Ka times Kb equals Kw, Kb equals to Kw divided by Ka. So that equals to 1.0 times 10 to the negative 14 for equilibrium constant for water divided by Ka. The Ka for the acid is 6.8 times 10 to the negative 4. That equals to 1.5 times 10 to the negative 11. Okay. For question B, we need to find Ka for ammonium ion. We need to find Ka for ammonium ion. So ammonium ion will have or we can say ammonium ion is conjugate acid of ammonia. Okay, then if we know Kb for ammonia, we can easily find Ka for ammonium. Okay, so according to this chart, 16.4, ammonia has a Kb value of 1.8 times 10 to the negative 5. Okay.
Dr. Lee, I have a question.
Mm-hmm.
If we have, for example, say a question like this on the exam, will this chart be provided for us, or is this something we need to memorize?
No, you don't have to memorize Ka or Kb value.
Okay,
Okay.
thank you.
Yeah, but then what, like I said before, if you see ammonia, pyridine, hydroxylamine, any nitrogen that has lone pair, do you remember this from the previous slides? Any nitrogen with a lone pair, these are going to have basic properties, right? That you have to know. So any atoms with bears lone pair electrons, non-bonding electrons, these will more likely to steal the hydrogen from the acid. That's why these have basic properties, right? Those things you need to know. Okay, but the specific numerical value of K and Kb, you don't have to memorize these.
Okay, thank you.
All right, so Ka times Kb equals Kw. So Ka equals Kw divided by Kb. Kw is always 1.0 times 10 to the negative 14. Kb is reported to be 1.8 times 10 to the negative 5. This equals to 5.6 times 10 to the negative 10. Okay. So that's that. Again, this formula can only be used for conjugate acid-base pair. Okay. All right, so as you can see from the previous sample exercise, we calculated Kb for the fluoride ion, and then ammonium ion. Okay, we calculated Ka and Kb for these ions. So this means many ions react with water to create proton or hydroxide. Okay, so any ion that react with water to create protons considered acidic, right? And then any ions that react with water to create hydroxide is considered basic. Okay, so this type of reactions where cations or anions react with water to generate proton or hydroxide, it's called hydrolysis. Okay. So cations or anions react with water to produce proton or hydroxide. It's called hydrolysis. Any salt dissolved in water is going to be in dissociative ionic form. Okay, and if this dissociated ion is reacting with water to increase proton concentration, it is considered an acid. Any salt dissolved in water in dissociated ionic form react with water to increase hydroxide concentration. Again, it's considered as a base. Okay, so cation cations in water, these can be acidic or neutral. Anions in water can be acidic or basic or neutral. Okay, let's take a look at acid-base properties of these cations and anions in more detail in the next few slides. Let's take a look at anions first. We are talking about acid-base properties of. Um, please let me know if the screen is frozen or it's not loading properly. Okay, we're talking about acid-base properties of salts. So we're talking about any salts that contain anions. Any salt that contains anions. Okay, these salts can be neutral, basic, or acidic. Be neutral, acidic. So before I start going over this slide, let me repeat the definition of a base. A base is a substance when react with water increases hydroxide concentration, right? Hydroxide concentration in the system. So whatever reactant that can react with water to steal the proton from water will generate hydroxide and increase the concentration of hydroxide. Okay, so that's the definition of a base. Okay, so keep that in mind. Firstly, let's take a look at anions of strong acids. Anions of strong acids. Okay, any anions of strong acids are neutral. This means these anions will not react with water. So therefore, no hydroxide is produced because there's no reaction with water. For example, chloride ion. This anion is a conjugate base of hydrochloric acid. This is a conjugate base of hydrochloric acid. Hydrochloric acid is therefore chloride ion, which is a conjugate base of strong acid, is an extremely weak base. Okay, we've learned this before already. Conjugate base of strong acid is a weak, extremely weak base. This chloride ion has basically a zero basic property. It is very, very reluctant to act as a base and steal the proton from water to generate hydroxide ion. Therefore, any salt that contains chloride ion will be neutral. Any salt contains chloride ion is going to be neutral.
Dr. Lee, I have a
Okay.
question.
Mm-hmm.
So when an ion steals a proton from water, then it makes hydroxide ions, making it an acid or a base. I'm sorry.
Um, so you were correct up till steal the proton from water.
Oh,
And
so
then
what
what
steals the
happens?
proton from water then?
Yeah, and then if water loses proton, what does it become?
Um, a base or an acid?
Hydroxide, not the base, hydroxide ion, right?
Oh, hydroxide. Okay,
Yeah.
and then
So if if water loses a proton, what does it become? Then if Cl increases the
in
concentration of hydroxide, then
yes.
it's considered as a base. But like I said, chloride ion has extremely low basicity. So it is very reluctant to act as a base to steal proton from water. So this chloride ion will not react with water. It will not steal proton from water. It will not increase the concentration of hydroxide. Okay.
Okay, thank you. That makes sense.
Mhm. All right. So therefore, any salt containing chloride ion, is chloride going to do anything with water? No. So therefore, any salt contains chloride ion. It's just going to be neutral. Okay. Secondly, let's take a look at salts containing anions of weak acids. Any anions of weak acids are weak conjugate bases. These anions will react with water to create hydroxide in water. It will increase the concentration of hydroxide. For example, acetate anion here. Acetate anion is a conjugate base of acetic acid. Acetic acid, which is a weak acid. Conjugate base of weak acid is a weak base. Okay, so therefore, this acetate anion, which is a weak base, it has some basic property, which is this anion is able to steal the proton from water and generate hydroxide ion, increase the hydroxide concentration of the system. So therefore, any salt contains this acetate anion, anions of weak acids. These are going to be weakly basic. Any salt contains acetate anion or anions of weak acids. Basic. Okay. Why? Why? Why any salt contains anions of weak acids are basic? Because these weak bases are able to steal hydrogen from proton from water and increase the hydroxide concentration. These anions are able to act as a base. Okay. Thirdly, for any salts that contain anions from polyprotic acids, okay, can be acid or base. That means if it can act as a base, acid and base, that means anaerobic, right? Amphiprotic. It can be either acid or base, depending on the environment. Do you guys remember what polyprotic acid is? polyprotic acid, these are acids with more than one proton. So let's take a look at, for example, you have hydrogen sulfide. This anion is a conjugate base of sulfurous acid. This is conjugate base of sulfurous acid. Sulfurous acid is a polyprotic acid because it has more than one proton. The conjugate base is still in protonated form. Protonated anions. Okay. After getting rid of one proton, it still has one proton left. That's why we say it's protonated anions. Okay. So for this anion, okay, any salt that contains this anion, is it going to act as an acid or base? It can act as both acid or bases depending on the environment. Okay. So if for these salts that contains these anions of polyprotic acids, if Ka is larger than Kb, then this ion will act as acid. If Kb is larger than Ka, then the ion will, okay, or in other words, any salts contain these protonated anions will be acidic if Ka is larger than Kb. Any salt contain these if Kb is larger than Ka. Okay, so depending on the situation, hydrogen sulfide or salt containing hydrogen sulfide can act as an acid or base. Okay. All right, let's take a look at any salts containing cations. Okay. Salts containing cations. Okay. Firstly, for salts containing group 1 and group 2 metal cations are going to be neutral. Okay. From the periodic table. So let's say, for example, sodium. Okay. Sodium is a group 1 metal. So any salt containing this group 1 metal, such as sodium nitrate, okay, this salt is going to be neutral. Why? Because it contains group 1 metal. So as you can see here, sodium nitrate here has a pH of 7. It is neutral. Okay, this salt is neutral when it's dissolved in water. Okay. Also, calcium is a group 2 metal. So any salt containing this group 2 metal, such as calcium nitrate, is also going to be neutral. Why? Because this salt contains calcium. As you can see from picture here, calcium nitrate has pH 6.9, very, very close to 7. It is also neutral in water. Secondly, any salt, any salt containing polyatomic cations are going to be weakly acidic. So ammonia, for example, okay? Ammonia, for example, is a polyatomic cation. This is polyatomic cation, okay? This cation is conjugate acid of weak base. Conjugate acid of NH3, which is a weak base. Okay, and then so according to the previous definition that we have learned, conjugate acid of weak base is weak acid. So this is a weak acid. Okay, so therefore this is a weak acid, and since ammonium is a weak acid, any salt containing this polyatomic cations will be weakly acidic. Why? Because it contains cation that is going to be weakly acidic. Okay, so I'm going to. I forgot to summarize this. So for the first one, any salt containing group 1 or 2 metal cation going to be neutral. Here, any salt containing polyatomic cation generally acidic. Okay. Thirdly, any salt containing transition and post-transition metals are going to be acidic. Let me see if I can bring a periodic table. We have a periodic table. So here's the periodic table, and then transition metals are going to be the metals in this region. Okay, look at the periodic table that I shared on Web Campus. You will have a better idea of the transition metal and basic metal. I don't want to go to Web Campus and bring that periodic table because I'm afraid the screen's going to get freeze. So I'm not going to bring that periodic table, but you guys should take a look at that periodic table. That periodic table has color coordination. It specific color for transition metal and the post-transition metal. Okay, so it's going to be easier for you to visualize. Okay, so any transition metal and any post-transition metal, if salt contains transition metal and post-transition metal cations, those salts are going to be acidic. Okay. So why? I'm going to explain why. So transition and post-transition metals such as iron 3 plus, zinc 2 plus, or aluminum 3 plus, for example. Okay, so any salt that contains these metals are going to be pretty acidic. Okay, so for example, in the picture here, zinc nitrate, aluminum nitrate are two salts that are acidic, pH pretty low. Why? Because these contains these transition metals. Okay. So what makes this metal possess acidic property? Why these metals have acidic property? This is because the definition of an acid is any substance when dissolved in water that increases proton concentration, right? These metals, when dissolved in water, they increase proton concentration, and therefore they are considered acidic. These metals increase proton concentration when dissolved in water, therefore considered acidic. Okay, I will explain to you why. Why? It has to do with charges. So these transition and post-transition, okay, I'm going to make a note here. Wait, for this, any salts containing transition or post-transition metals are going to be acidic. All right, let's focus on why these metals increase proton concentration when dissolved in water. These cations are positively charged. Of course, because they are cations, okay? And when these positively charged cations are in water, the positive charge of the metal will attract the lone pair electrons of the water. Okay? These are electrons, right? Pretty negatively charged because of the electron density. So the positively charged metal will attract these lone pair electrons of the water. This is not a reaction, but it's more like a coordination where they come closer together. It's like a coordination. Okay. Then eventually, due to this coordination, the hydrogen of the water will eventually fall off, increase proton concentration. Okay, this OH part is going to remain coordinated form with the metal. Okay, so now they're separated. Okay, so now this iron and hydroxide, they stay closer together, and hydrogen eventually falls off. Okay, so due to this reason, any salt containing these transition metals or post-transition metal will be acidic because they produce a proton. They increase the proton concentration when they're in water. Okay. This is a table of acid dissociation constants for metal cations in water. Okay, so these are the metals. The stronger the positive charge on metal will attract more water molecule more strongly, right? The more positive the metal, the more the attraction to this negative lone pair electrons that are going to be more stronger, okay? Therefore, generate more proton. So as you can see, compare iron 2 plus and iron 3 plus. Which is a stronger acid? Iron 3 plus is stronger acid because it is more positively charged. Okay, the more positively charged iron attracts this lone pair better. Hydrogen falls off easily. Concentration of hydrogen increases more readily. Therefore, it is considered more stronger of an acid. Okay, so here is a summary of how to predict whether salt containing cations or anions are acidic, basic, or neutral. Okay, so salt contains both cation and anion. Salt contains both cation and anions. The bottom line is that you have to look at which cation or which anion, will affect or influence the pH. The question is, which cation or anion will affect or influence the pH of the system? Okay, so let's take a look at um, the first situation. If you have salt with group 1 metal cation, and anion of a strong acid, which one will have influence on pH? As we've seen before, group 1 and group 2 metal cation has no influence on pH. So I'm going to write no influence on pH. But the anion of a strong acid, anion of a strong acid also has no influence on pH. Okay? So then the salt that contains group 1 metal cation and anion of strong acid, this combination of the cation and anion salt is in result it's going to be neutral. Okay, so the overall salt solution will be neutral. Overall salt solution will be neutral. Neither cation nor anion are affecting the pH of the system, as they both have no influence on the pH of the system. Okay, let's take a look at the second situation. The second situation, you contain group 1 2 metal cation and anion of a weak acid. As we already know, group 1 and 2 metal cation has no influence on pH. How about anion of weak acid? Does it have influence on pH? Yes. Anion, um, okay, anion of weak acid is going to be basic. Mm, yep. So the overall salt solution will be basic. Why? Because it contains anion of weak acid. Overall salt solution will be basic due to the presence of this anion of weak acid. Let's look at third situation. In third situation, you have a cation from transition and post-transition metal, and or you have polyatomic cation, and for the anion, you have anion of strong acid. Transition post-transition metal cation or polyatomic cation has influence on pH. These will make aqueous solution acidic. Okay? How about anion of strong acid? Anion of strong acid will have no influence on pH. Okay? So what happened to the general overall salt solution? Overall salt solution is going to be acidic. Why? Because of the presence of these metal or polyatomic cation. Okay. The fourth situation, you have transition post-transition metal cation or polyatomic cation, and you have anion of weak acid. Again, transition and post-transition metal cation, polyatomic cation, they definitely have influence on pH. We know that they have acidic influence, right? Anion of weak acid, anion of weak acid also has influence on pH. These will make the solution basic. Okay, so in this case, you have to compare the Ka and Kb. Okay, again, if Ka is larger than Kb, the overall salt solution is going to be acidic. If Kb is larger than Ka, um, overall salt solution is going to be basic. Okay. Let's try a sample exercise. Let me know if anyone needs me to go back. Okay.
Yeah,
Great,
All
can
Professor,
you
right.
go
can I
back for a
actually?
second?
Oh yeah, sure.
Thank you.
Hmm. Let me know when you guys are done.
Are you going to be uploading the written notes to Canvas for chapter 16?
Yeah, once I'm done with the chapter.
Dr. Lee, could you just explain again why the transition and post-transitional metals are basic and why the polyatomic cation of that is acidic?
No, I didn't write basic. Transition and post-transition metal cations are acidic.
Oh, sorry, I was
Acidic.
reading the wrong thing.
Yeah.
Okay, I'm done. Thank you.
Remember here, back here, these transition and post-transition metal, they are positively charged. They are going to attract water molecule. Why? Because water molecule has this lone pair electrons. Electrons are pretty negatively, partially negatively charged, right? So this is like a partially negative charged region. Negatively charged region is going to be attracted to this positively charged metals. So what happens is the water molecules are going to come close, 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 close to this iron, and eventually what's going to happen is the water is going to fall off. So if hydrogen, not water fall off, hydrogen falls off. If hydrogen falls off and increases proton concentration, did this act as an acid or base? Acid, right? Because it increase the proton concentration. Okay, so transition and post-transition metals are going to be acidic in water. They're going to make the solution acidic. So let's try a sample exercise. Determine whether aqueous solutions of each of these salts are acidic, basic, or neutral. Okay, for question A, you have barium acetate, ammonium chloride, methyl ammonium bromide, potassium nitrate, aluminum perchlorate. You have to determine whether these salt solutions are going to be acidic, basic, or neutral. Again, in order to determine whether salt solution containing these salts are basic, acidic, basic, or neutral or not, we need to determine whether cations and anions affect the pH or not. Okay, so let's take a look at the barium acetate first. Barium acetate. Barium. What do you have as a cation? Barium, right? Okay. Cation. Cation is barium. Barium is a group 2 metal cation. Group 2 metal cation. Does group 2 metal cation has any influence on pH? According to the previous slides, no. So no influence on pH. What do you have for the anion? You have acetate for the anion. This anion is an anion of weak acid, right? Anion of weak acid. Or in other words, this is a conjugate base of weak acid. What properties does conjugate base of weak acid have? They are basic, right? Weakly basic. So it has influence on pH. Has influence on pH. What influence? Basic influence, right? Anions of weak acid, conjugate base of weak acid are weak base, okay? So the overall salt solution is going to be basic. the acetate will have basic influence. And I'm just going to write basic. Has influence on pH. So overall salt solution is going to be basic. Why? Because of the presence of this acetate anion. Question B, you have ammonium chloride. So what is a cation? You have NH4 plus cation. This is a cation of a weak base. Cation of weak base. Or in other words, this is a conjugate acid of weak base. What properties does conjugate acid of weak base have? What properties does cation of weak base have? They're weakly acidic, right? So this anion, this cation will have acidic influence in the aqueous solution. What do you have for anion? You have anion chloride as an anion. Chloride is a anion of strong acid. Okay, anion of strong, or you can say conjugate base of strong acid. Okay, so does what properties does conjugate base of strong acid has? They have almost zero basic property. They have zero, almost no capability of stealing proton from water. Okay, so does chlorine has any influence in the aqueous system? No. No influence on pH. Okay, it's just gonna have neutral effect. No influence on pH means neutral effect. Okay, so so then the overall salt solution is going to be acidic. Why? Because of the presence of this ammonium cation. Okay. I am out of space. Okay. I'm sorry, but I have no space, so I have to make it really, really small. All right, let's take a look at C. For C, you have methyl ammonium bromide. CH3NH3Br. As for the cation, you have methyl ammonium. Okay, this is a cation of weak base, or other words, conjugate acid of weak base. What base? This is a amine. Okay, so this is a cation of weak base. Okay, so then what effect does conjugate acid of weak base have in aqueous solution? They will have acidic effect. Acidic effect. Okay. What do you have for the anion? As for the anion, you have bromide. This is an anion of strong acid. Okay. Or conjugate base of strong acid. What effect does conjugate base of strong acid has? It will have no effect on pH. It will have neutral effect. Okay. Conjugate base of strong acid has basically no basic property. Okay, so no influence on pH. Okay, so what happened to the overall salt solution? Overall salt solution is going to be acidic. Why? Because of the presence of this cation, which has acidic effect. Oops. Okay. Question D is potassium nitrate. For this salt, you have potassium as a cation. Okay, potassium is a group 1 metal cation. Group 1 metal cation. It will have no influence on pH. Okay, for the anion, you have nitrate. Oops. Oops. Nitrate. Nitrate is anion of strong acid. Okay, or conjugate base of strong acid. Okay, again, conjugate base of strong acid has no influence on pH. So therefore, the overall salt solution is going to be neutral. None of the cation or anion are having influence on the pH of the system. Okay, question E. You have aluminum perchlorate. As for the cation, you have aluminum, which is a post-transition metal cation. Post-transition metal cation. It will have acidic influence on the pH, right? It will make the system more acidic because it increases the proton concentration, right? So it will make the system more acidic. It has acidic influence. As for the anion, you have perchlorate. This is anion of strong acid. Okay, so if you want to know whether this anion is anion of strong acid or no, put an H and then go back to the table, the strong acid and strong base table. See if these are the protonated version, the acidic version of these are strong acid or not. So you have to go back to those tables. Okay. So anion of strong acid, or in other words, conjugate base of strong acid. Okay, again, conjugate base of strong acid has no influence, right? No influence on pH. So therefore, overall salt solution is going to be acidic. Why? Because of the presence of this post-transition metal cation, which has acidic influence on the system. Okay, let's try a sample exercise where salt contains protonated anions. These are going to be a little bit more challenging type of exercise. We don't have much time, but we'll try the best we can. Okay. So predict whether salt disodium hydrogen phosphate forms an acidic solution or a basic solution when dissolved in water. Disodium hydrogen phosphate has cation that is a group 1 metal, which has no influence on pH. How about anion? The anion is going to be hydrogen phosphate, which is a protonated anion. Protonated anion. So this anion is from polyprotic acid. Okay, so this will have influence on pH, but we have to compare the Ka and Kb value to see whether this anion act as an acid or base. Need to compare Ka and Kb. We don't know whether this anion is going to have acidic influence or basic influence to the aqueous solution yet. So let's write a chemical equation when this anion act as an acid. HPO4 act as an acid. If it's going to act as an acid, it's going to generate proton, right? It's going to generate proton, and it's going to generate this anion, deprotonated version of the anion. So because it's acting as an acid, it will lose the proton or give up its proton to increase the proton concentration and phosphate ion. If we look at table 16.3, where it lists all the polyprotic acids, I'm going to quickly go back to that table. Copy. Can you guys see this table?
Yes.
Okay. Yeah. So according to this table, if you focus on this part, losing hydrogen of phosphoric acid, losing hydrogen of this, losing the third hydrogen of phosphoric acid is will basically generate this. So therefore, the Ka value for this reaction Ka value is going to be this acid dissociation constant of losing third proton of phosphoric acid. Okay, so the Ka is going to be 4.2 times 10 to the 13. So now that's that, and let's write an equation where this anion act as a base. If the anion is acting as a base, it will steal the proton and it will generate hydroxide anion, right? It will steal the proton and it will have H2 now. and it has successfully increased the hydroxide concentration because this anion stole the hydrogen of the water. Okay, so what's going to be because this is a reaction in base point of view, we want to find Kb. However, we don't know Kb, but we can find Kb using Ka information. Remember, the Kb is basically Kw divided by Ka. Okay, so what is Ka? These two are conjugate acid-base pair. Ka is acid dissociation constant. So you want to determine what is an acid in this equation. Of course, this is going to be the acid in this equation, a protonated form. Okay, so since hydrogen phosphate is an acid, we can find Ka of this acid, and with that information, we can find Kb of the conjugate base. Why? Why can we do that? Because they are conjugate acid-base pair. Okay, so let's find the Ka. These are conjugate acid-base pair. Okay, so Ka of this acid is going to be losing the second proton from phosphoric acid, which is Ka2. Okay, so the Ka for this is going to be 6.2 times 10 to the negative 8. Okay, then Kb is going to be basically Kw divided by Ka. Kw is always 1.0 times 10 to the negative 14 divided by 6.2 times 10 to the 8. Then you have Kb value of 1.6 times 10 to the negative 7. So now we have Ka value and Kb value. Which one is larger? One is 10 to the power of negative 13. One is 10 raised to the power of negative 7. Definitely this is larger. So because Kb is larger than Ka, this anion will act as a base. Will act as a base. Okay, so predict whether this salt act as a base or acid in aqueous solution, right? This salt is going to act as a base. Why? Because it contains anions that act as a base. Okay. All right, so that's the end for today's lecture. I'm going to hang around for another 5-10 minutes just in case anybody else has questions. Okay. Sorry for going over time.
Dr. Lee,
Yes.
could you go over the what you just went over right now one more time? I'm just a little bit confused about how you determine um how which value is bigger, the Kb or the Ka, and how that makes it an acid or a base. If you could just describe that quickly. Thank you.
Mm, Um, wait, which part? Comparing KB and Ka, this part?
Yes, and then also, how do you determine that it's a base or an acid? How it acts as a base or an acid?
Uh, okay.
Like what makes it act as an acid and what makes it act as a base?
What makes it act as an acid? What makes it act as a base? Oh, um, so the oh, if the acid dissociation constant is larger, what does it tell you? Let's say you have two acids. One has larger Ka value. What does it tell you?
If it
Is
has
it
a larger Ka value, then it will
mm-hmm.
act as an acid.
Yeah, so like if you have two acids
Mm-hmm.
and one has higher Ka value, larger Ka value, then that's a strong acid, right? Stronger acid, right?
Yes, and if it
Does
has a lower value, it's a weak acid?
yeah, weaker acid, right? So
Okay.
acid dissociation constant basically tells you how readily the proton is going to fall off.
Okay.
The higher Ka value, the proton is going to more easily fall off. Does that make sense?
Yeah, that makes sense. And then
Or
more.
in other words, it means higher Ka value.
Mm-hmm.
Higher Ka value means more protons are generated. More
Okay.
protons are generated. Why? Because the protons were easily falling off, right? Does that make sense?
Yeah, that makes sense.
What about Kb? Same thing for Kb. The higher Kb value, more likely that this compound is going to produce more proton or hydroxide?
Hydroxide.
Hydroxide, okay? So now here you're comparing Kb value, and Ka value.
Okay.
Kb value is definitely larger, right? If you compare the numerical value, 4.2 times 10 to the negative 13 versus 1.6 times 10 to the negative 7, which number is larger?
The Kb value would be larger.
Larger, yeah. So this value larger means, what does it tell you? Kb value larger means this anion is going to
Act as a
more likely to produce more hydroxide ion in water. Does it make sense?
Yeah, that makes sense.
Yeah. So therefore, rather than this anion act as an acid, it will rather prefer to act as a base.
Got it.
Does that make sense? Yeah.
That makes sense. Thank you.
Mm-hmm.
I have a question.
Uh-huh.
When you see the formula, how can you identify which one is a cation and anion?
When you see a formula, how can you determine which one is a cation, which one is an anion?
Yes.
Like if you see this formula, oh, so in order to determine which one is a cation, which one is an anion, you should go back to chapter 2, and there were lists of cations and anions I asked you to memorize. Okay, I know memorization is boring, it's hard, but as I already mentioned before, if you have those memorized on top of your head, the rest of the course is going to be very, very easy. And then it's going to be easier for you to, for like biochemistry in the future, organic chemistry in the future as well. Okay, so try to go over chapter 2 one more time. Okay, how to distinguish cation and anion. Okay.
Thanks.
Mm-hmm.
I have a question.
Mm-hmm.
Would you well first can you please like zoom in to like the K values that you have in like that little chart, please?
Yeah, if this is hard to see, you can go back to few slides back and then look for table 16.3 or put a note on your paper to go back to table 16.3.
Okay, thank you.
And
And then
yeah,
also how did you know which K value to use because there's 3?
yeah, so what's Ka? Acid dissociation of first proton, the dissociation of first proton, right?
Yeah.
What's Ka2? Dissociation of second proton, right?
Yes.
So after first deprotonation, you will have H2PO4. After another deprotonation, you will have HPO4, and then another deprotonation, you will eventually have PO4. Oops, 2 minus. This is minus, and then 2 minus. This is 3 minus. Okay, so is that clear, or do you want me to
Oh
further
yeah, it is.
explain?
Thank you.
You got it?
Yes,
Okay.
no, it's clear. Thank you.
Mm-hmm.